Hello everyone, this is Dheeraj with roll number 23BQ100454 with my seminar topic double sideband suppressed carrier, in short DSBSC. What is DSBSC? It's a type of amplitude modulation where we take the carrier signal, the part that usually just sits there waving at you, and suppress it, leaving only the two sidebands that carry the actual message. Think of it like sending a letter without the envelope. Less waste, more focus on what matters. So DSBSC saves power and makes smarter uses of bandwidth, which is a big deal in communication systems. Today we'll explore what it is, how it works, and most importantly, how we generate it. So let's get started. Uh, So in conventional AM, it is observed that in modulation signal, we have full frequencies. We have frequencies like FC, FC plus FM, and FC minus FM. So where FC is carrier frequency, which is not having information, and FC plus FM and FC minus FM are sideband frequencies which have information. For transmitting DSB-FC, 66.6% of total power is used for transmitting carrier component, which doesn't have any information, whereas only 33.3% of total power is used to transmit sidebands, which actually have information. It is observed that 66% of total power is being wasted for transmitting carrier. So to overcome this problem, we go for double sideband suppressed carrier where carrier is suppressed before transmitting through the transmitter. So let us see the time domain representation of double sideband suppressed carrier. When the carrier is suppressed during modulation process, the result is only the algebraic sum of upper and lower sidebands. So the standard equation of DSBSC is given by S of t equals AC into 1 plus Ka m of t into cos 2 pi FCT. So in general, message signal and the product of message signal and carrier signal is given by DSBSC. It is represented as S of t equals m of t into C of t, where m of t is am cos 2 pi fmt and C of t is given by AC cos 2 pi fct. So by multiplying the message and carrier signals, we get S of t equals AM into AC by 2 into cos 2 pi FC plus FM into T plus cos 2 pi FC minus FM into T. We only have two frequency components, FC plus FM, which is upper sideband frequency component, and FC minus FM, which is lower sideband frequency component. So let us see the frequency domain representation of double sideband suppressed carrier. As we all know, the time domain representation, as we have seen right now, which is S of t equals ACAM by 2 into cos 2 pi FC plus FM into t plus cos 2 pi FC minus FM into t. By applying the Fourier transform, we get the Fourier transform of cos 2 pi FCT is half into del of f minus fc plus del of f plus fc. So by that equation, we get s of f equals ac into am by 2 into half del of f minus fc plus fm plus del of f plus fc plus fm plus del of f minus fc minus fm plus del of f plus fc minus fm. So the frequency spectrum is given uh, as we can see here. So now let us see the generation techniques of DSBSC. There are two generation techniques of to generate DSBSC. So one is balanced modulator. So let us dive into balanced modulator. It is used to suppress the carrier signal from amplitude modulated signal. Principle used in balanced modulator. When two signals at different frequencies are passed through a nonlinear resistance, AM signal is generated with suppressed carrier, and this nonlinear device is such as diode, JFET, and transistor. As we can see, there are two AM modulators with message signal, and there is a sign reversal of message signal, and there is an oscillator which gives carrier signal, and the DSBSC is produced. Uh, so as you can see, the diagram of a balanced modulator. Both message signal, modulating signal and carrier signal are provided to the balance modulator, and DSP-SC is produced. So this is the block diagram of balance modulator. So the balance modulator circuit consists of two AM modulators, as we have discussed earlier, which are arranged in balanced configuration to suppress the carrier. And the two modulators are identical except for the sign reversal of M of t. The outputs of modulators can be given as S1 of t equals AC into 1 plus Ka m of t into cos 2 pi fct, and S2 of t equals AC into 1 minus Ka m of t into cos 2 pi fct. So S of t equals S, we need to add these. So S1 of t minus S2 of c, S2 of t, as we have the sign reversal. So S of t is given as 2AC cos 2 pi fct into Ka m of t. So S of t equals 2 Ka m of t into C of t. The balance modulator output is equal to the product of modulating and carrier signals. So this is all about balanced modulator. So now let us see the second type of DSP-SC generation technique, which is ring modulator or diode modulator or lattice modulator. So the ring modulator consists of four diodes. D1, let us assume the diodes has D1, D2, D3, and D4, and two transformers T1 and T2 connected in a bridge circuit. The diode connected in the bridge acts like switches and are controlled by a carrier signal because carrier is generally higher in frequency and higher in amplitude when compared to the message signal M of t. For positive half cycle of carrier signal, let us assume the modulating input is 0. In this mode, the diodes D1 and D2 are in off condition, and diodes D3 and D4 are in off. Diodes D1 and D2 are in on condition, and D3 and D4 are in off condition. So the current divides equally in upper and lower portions of primary winding of the transformer. This current produces magnetic field which is equal and opposite in upper and lower parts of the winding. Hence, they cancel each other and produce no output at the secondary of transformer T2. Hence, the carrier is suppressed. So the reduced diagram when diodes D3 and D4 are off is given by this. So now let us see the negative half cycle of ring modulator. For negative half cycle of the carrier, D1 and D2 are reverse biased, D3 and D4 are forward biased. So D1 and D2, as they are reverse biased, they are removed. So similar to positive half cycle, the magnetic field in primary winding of transformer T2 are equal and opposite. So they cancel each other, making the output as 0. So the suppression of carrier in both half cycles depends on diode characteristics and exactness of center tap transformers. So now let us see the ring modulator with a modulated signal included. So let us consider a low frequency sine wave M of t applied to primary winding of transformer 1. The balance modulator works perfectly when the carrier signal is a square wave. Uh, So the Fourier series representation of C of t is 4 by pi into sigma n equal to 1 to infinity minus 1 whole power n minus 1 by 2n minus 1 into cos 2 pi fc 2n minus 1 into t. So as we know that S of t equals m of t into C of t, which equals m of t into 4 by pi into sigma of n equals minus 1 to infinity minus 1 into n power minus 1 whole power n minus 1 by 2n minus 1 cos 2 pi fc 2n minus 1 into t, which equals 4 by pi cos 2 pi fct by substituting the values of n according and applying sigma, we get 4 by pi cos 2 pi fct minus 1 by 3 cos 6 pi fct plus 1 by 5 cos 10 pi fct and so on into the modulating signal m of t. So we know that cos 2 pi fct, the Fourier transform of cos 2 pi fct is half del of f minus fc plus del of f plus fc. So the modulation property f of x of t into cos 2 pi f ct, uh, which equals half into x of f minus fc plus x of f plus fc. As there is modulating signal, we apply the modulating property out here. So after applying Fourier transform, we get S of f equals 2 by pi into m of f minus fc plus m of f plus fc minus 2 by 3 pi into m of f minus 3fc plus m of f plus 3 fc. So by eliminating higher frequencies, S of t is given by 4 by pi into modulating signal m of t into cos 2 pi fct. So let us consider it as equation 1. And S of f equals 2 by pi into m of f minus fc plus m of f plus fc. And the spectrum is given as we can see here. So from equation 1, it is observed that we have generated the DSB-SC, which is 4 by pi into modulating signal m of t into cos 2 pi fct. So now let us see some of the advantages and challenges or disadvantages of the double sideband suppressed carrier. So the advantages are it's power efficient and consumes less energy which is wasted on the carrier, and it uses bandwidth smartly since all the focus is on the sidebands. That's a win for any system where power or spectrum is tight. But there are some challenges. Without the carrier, the receiver needs a synchronized local oscillator for coherent detection. If that is off, your signals will toast. That's why DSB-SC is not as common as AM in everyday stuff like car radios. It's a bit more demanding. Where does we see DSB-SC in our regular life? You will see it in analog TV for video signals, early stereo FM experiments, or even educational setups where engineers play with modulation. It's a stepping stone to more advanced techniques too, like single sideband modulation. So now, now let us recap all about the double sideband suppressed carrier. So DSBS is a modulation technique that suppresses the carrier to save power brought to life by balanced modulators, ring modulators, and analog multipliers. It's efficient, it's clever, and it's a key piece of communication history. So next time you tune into a signal or design one yourself, think about what's not being sent. That's the magic of DSBSC. So thanks for watching. Thank you, everyone.